Alrighty, in this last video for chapter 5, we're going to be going over 4.5, which is probability and counting rules. So putting it all together with the permutation, combinations, and the total options there are as well with an event happening. So in objective 8, we're going to find the probability of an event using the counting rules. Now that we have learned the fundamental counting rule, the permutation rule, and the combination rule, it is possible to now compute probabilities of outcomes of many experiments. So let's look at example 26 here. Scheduling workers. So suppose a manager supervises 16 women, 12 men. Each shift needs 8 people. So let me see if I can do this. I'm going to restructure this. So maybe I can get all the questions on there. But I think I'm trying to think here. I think it does it all for you. Um, it isn't any fun. I like to break it down with you. So I think that's what I'm going to do. So I'm going to put most of my work on this page here. You can see a breakdown of the things you kind of want to work through. The issues with this is, again, you got to determine, does order matter? If order matters, then we're selecting a group to work a shift. If order doesn't matter, then it's going to be a combination. So if order matters, permutation; order doesn't matter, combination. All right, so here we go. We want to find the probability that exactly 3 women are selected to work this shift. So for starters, see it goes again. So suppose a manager for supervisor has 16 women, 12 men. Each shift gets 8 people. So if I want exactly 3 women, that means I need 5 men. So to start off, I need to find how many possibilities are there to get exactly 3 women. So this would be a combination because as long as they're women, it doesn't matter if the woman's first, second, or third, they're still women. So in this case, to find 3 women, I'll do 3 factorial over let's see. So there were 16 women. So that'd be 16 minus 3 factorial times 3 factorial. That comes out in the calculator as 560 combinations, pulling 3 women out of 16. The other one has to be 5 men. So that would be 5 factorial. Oh, not 5. Hold on. This would be 16. And there is 12 men. So this would be 12, and then 12 minus 5 factorial times 5 factorial. And all right, I guess I got y'all back. All right, that was weird. It just kind of stopped working. All right, so I have to write all this work back. So again, this would be for 3 women. That would be again 16 women in total over 16 minus 3 factorial times 3 factorial. And again, that comes out as 560. 5 men exactly. So that would be 12 men out of 12 minus 5 factorial times 5 factorial. And that would give me about 792. We're going to find how many ways 8 people can be selected from the total of the 28, right? So if I want to find exactly 3 women, I need 8 of them to be chosen. So that now would be 8 people, right? So that would be then 28 options over 28 minus 8 factorial times 8 factorial. See, the order doesn't matter. That comes out to about 3,108,105. This will be pretty much the number we use all the time. So now all I got to do is find out all the different possibilities of it getting exactly 3 men and 5 men. So all I got to do is do 560 times this 792. And when I do that, I get 44,300 and oh, my bad, 443,520 right there. So that is all the possibilities I have out of 3 million. So to find this out, I now just take that, divide it by 3.108, basically 3,108,105. When I do that, I get about 0.1427. So I have a 14.27% chance that exactly 3 women will be selected out of 8 for an 8-person shift out of 28 people. All right. Part B, saves this up, says find the probability that no women are selected to work the shift. All right. So again, if I'm looking for no women, that means 8 of them would be man. All right. So I come over here. So I do 8 men. So that would be 12 factorial. 12 minus 5 factorial. Not 5. 8 times 8 factorial. And this actually comes out to, for 8 men, 495. All right, so that's my total option. So that will now be 495 to have 8 men selected out of the total amount of options there were. So 3,108,105. And that comes out to about 0.0002. So you have about a 0.02% chance that all 8 of them are men on the shift, which means that none of them are women. Part C, it says now find the probability that all the people selected to work the shift are women. So this time I want the probability of them all being women. So 8 women. So let me do this in a different color now for a different part of the process. So 8 women. That would mean that that would be 16 to choose from. So that'd be 16 minus 8 factorial times 8 factorial. And when we do that, that's 12,870 options. So again, probability of the people selected to work are all women. So now that's going to be the 12,870 over the 3,108,105. And we do that, we get about 0.0041. So you have about a 0.41% chance that the entire shift is women. The last part here is find the probability that at least one woman is not selected to work the shift. So remember to find at least one, that's the same thing as saying 1 minus the probability that you select none. So if we want to know the probability of at least one woman, let's find the probability that none of them are women, which we've already done, which is the 0.002 there. So I'm just going to do 1 minus the 0.0002, and they actually come out to 0.9998. So there's a 99.98% chance that at least one woman is put on the shift. All right, so again, they really break it down in your notes, but I thought it'd be better if we just did it together as well. But it goes all the way through in detail as well. But with that, let's look at another problem. So again, here is all the work in words for your convenience. So let's look at example 27. It says there are 5 houses and a cul-de-sac in a deed-restricted neighborhood. It is time for all the houses to be painted. The homeowners association has approved 3 colors of paint: beige, blue, and yellow. How many different color sequences might be chosen to paint the houses? So the best way to do that, there are, figuring out how many there are. There's 5 houses and 3 colors. So the first house has 3 options. The second house has 3 options. The third house has 3 options. The fourth house has three options, and of course, the fifth house has three options. So this ends up just really being power of five. So let's do that in the calculator, and that comes out to 243 different combinations of colors for these five homes. Part B then says, what is the probability that all five houses would randomly select the same color? All right, so now that I know there's 243 houses, so that's 243 houses, they can either all select beige, so that's one. They can all select blue, that's another. And they can all select yellow, that's another. So there are only actually three different ways that they can all pick the same number out of the total of 243 options. When you plug this in the calculator, it comes out to 1 over 81, which is about a 0.0123. So they have about a 0.1, so they have a 1.23% chance that they all select the same color. Alrighty, let's look at another example. All right, let's look at example 28. So it says a decorator is selecting colors for the den walls, the sofa, and the accent chair. She can choose from 10 colors for the walls, 5 colors for the sofa, and 3 colors for the accent chair. Accent chair sounds decorative. Not my cup of tea. All right. So if I want to know how many ways to choose the colors, this is the fundamental rule of counting. I have 10 options for colors of walls, 5 colors for sofas, and 3 colors for this chair. So I have 10 times 5 times 3. So I have 150 different combinations to choose from with just that information. Part B then says, well, what is the probability that if colors are randomly selected, she chooses seafoam green walls, yellow sofa, and turquoise chair. Right? I have no idea how many color choices there were, other than the fact that there was 10, 5, 3. I'm going to go with, for this option here, this can only be one of the ways. Seafoam green wall, a yellow sofa, and a turquoise accent chair. That is one of the 150 ways. So in my eyes, that is her probability. So 1 out of 150. Had it said more or less that was the randomly that she chooses seafoam green wall, then we could have done a little bit more math. But this would looks like it's one of the 150 combinations that she could have chose from. All right, let's look at the next example. Look at example 29, selecting seminar attendees. In a company with 9 executives, of which 4 are women and 5 are men, 3 are selected to attend a management seminar. All right, so here we go. So let's circle what's important. So in a company, there's 9 executives, 4 are women, 5 are men, 3 are selected to go to this management seminar. So part A says find the probability that all 3 selected will be women. All right, so to do that, again, that doesn't matter the order. If she selected first, second, or third, they're all women, so they all get chosen. So order is not going to matter, so this will be a combination. So for this one, there are 4 women. So I'll do 4 factorial over 4 minus, I can choose 3 of them. So that's 4 minus 3 factorial times 3 factorial. That actually comes out to 1 factorial, so that should just come out to 4. So there are 4 ways 3 women can be chosen. And then we just need to know the total options. So the total options would be 9 executives, and I want to select 3 of them. So that's going to be 9 minus 3 factorial times 3 factorial. And when we do that, we get 84 options. So for this one, this would be 4 out of 84, which comes out to 1 of 21, which is about 0.0476. So there's a 4.76% chance that all three women are the ones chosen for this seminar. Part B says find the probability that all three selected will be men. So the only thing now I got to do differently is there's now 5 men, so that's 5 factorial over 5 minus 3 men can be selected times 3 factorial. So again, that would be 2. So that would be 5 times 4, which is 20. By 2, that should be 10 ways. So we get 10 ways to choose 5 men. And then we already know the total. So this is now 10 out of 84, which comes out to about 5 out of 42, which is about 0.1190. So there's a 11.9% chance that all three will be selected as men. This next one says find the probability that at least one of the people will be man. So remember, the probability of one, at least one, is equal to 1 minus probability of none. So if I wanted this, to at least one man, the probability that them all being girls would be 1 minus 0.0476. And when you do that, you come out to 0.9524. So there's a 95.24% chance that at least one man gets to go to this seminar. Part D, find the probability that 2 men, 1 woman will be selected. All right, so 2 men and 1 woman. All right, so in this case, I have to do a little bit more different math again. So I have to do, for the men, that's going to be 5 factorial over 5 minus 2 factorial times 2 factorial. When you do that, it still comes out to 10 ways. Again, that would be 3, still knocking out. Yep. All right, and then on the flip side, I would have for my women, so that's 4 factorial over 4 minus 1 factorial times 1 factorial. So that actually comes out to 4 ways again of choosing 1 woman. So there's 4 ways to choose 1 woman, 10 ways to choose 2 boys. If I want this to happen, and means to multiply, so that's going to be 10 times 4, which is 40 out of the 84 possibilities. So that is about 10 out of 21, which comes out to be about 0.4762. So there's a 47.62% chance that you get 2 men, 1 woman. Last probability here, find the probability that 2 women, 1 man. So again, we do the math. This time I'll do the women first. That's 4 factorial over 4 minus 2 factorial times 2 factorial. This time I actually get 6 options to pick 2 different women. And then for the men, this will be 5 factorial over 5 minus 1 times 1 factorial actually comes out to 5. So I have 6 options to pick 2 women, 5 options to pick 1 man. So this time it'd be 6 times 5, which is 30. Divide that by 84. I actually get 15 out of 42, which is about 0.3571. So there's now a 35.71% chance that I get 2 women, 1 man to go to this seminar. All right, let's do another example. Make sure you got plenty of examples going into your homework. So in example 30, we're going to be selecting lottery numbers. So in the lottery game, one selects a 3-digit number with repetition of digits per minute. We want to find what is the probability that all the digits are the same when the winning number is selected. So, so all the digits are the same when winning the number is selected. So there are 3 digits out of 0 through 9. 10,000. I lied. Don't know where my comma's supposed to go. That's 1,000. All right, I wrote the 3 zeros, but added another zero. So there are 1,000 different ways to make this combination of 3 digits. So before I want to find all the digits are the same when the winning number is selected. So they can all be zero, all be 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means there's actually 10 different ways that they could all be the same digit. So that'd be 10 out of 1,000. So that comes out to about 0.01. So there is a 1% chance that all three numbers are the same. Part B, a person's favorite 3-digit number is selected. So out of 1,000, there is one perfect number for that person's digit. So that's 1 out of 1,000, which comes out to 0.001. So if you have a certain number that you like, you have a 0.1% chance of winning a pick 3 lottery. All right, let's look at another example. So gift basket contents. Says the gift basket department at a local upscale grocery store has pre-made gift baskets containing the following combinations in stock. Well, there's F. I'm not able to get E and F in. It's all right. I got to figure it out. All right, so the gift basket department at a local upscale grocery store has the pre-made thing. So we have coffee, tea, cookies, mug, candy. So if they did coffee and cookies, there were 20 of those. Coffee and mugs, 13. Coffee and candy, that was 10. Tea and cookies is 12. Tea and mugs is 10. And tea and candy is 12. We want to find the probability that if one basket is chosen at random, it contains coffee or candy. So we need to do a few things. One, we need to find the total. So this would be 20, that'd be 32, 23, 22. That would be 45, 77 total. This would then be 20, 33. This would be 43, 22, 22 plus 12, 34. So there we go. So that's 30, 77 as well. So there's a finished thing. So if one basket is chosen at random and it contains coffee or candy, so that means we can add. So coffee or candy. So if it does coffee, that's 43. Or candy, that is 22. But now remember, we need to also subtract that if they're coffee and candy. So this is the probability of coffee plus the probability of candy minus the probability of both. So I'm going to subtract, let's see, coffee and candy was 10. So 43 plus 22 minus 10 comes out to 55. So there's 55 options that either coffee or candy. Divide it by the total 77 options. So that comes out to be about 0.7143. So there's a 71% chance that your basket will either have coffee or candy in it. Part B now says if one basket is chosen at random, it contains tea, given it contains mugs. So this one's a little different. So given means that I go to it being given. So there were 23 of them that had a mug. So that would be the new number on the bottom. Now, what's the probability that you get tea and mugs? So that would be 10 right there. So that'd be 10 out of 23, which now comes out to be about 0.4348. So 43.4% chance that your bag will contain tea given it had a mug in it. Part C, If one basket is chosen at random, it contains tea and cookies. So the one basket is chosen at random. It contains both tea and cookies. So when it does that, I go to tea and cookies. That would be the 12. So in this case, that would be 12 out of 77, which comes to be about, let me type in the calculator real quick. 0.1558. So about a 15.58% chance that you'll get both tea and cookies. Part D, if 3 baskets are chosen at random and not replaced, um, all of the baskets contain mugs. So if 3 baskets are chosen, not replaced, all baskets contain mugs. So this is going to be, let's see, they contain mugs. That would be, so if 3 baskets are chosen at random, not replaced, all the baskets contain mugs. There's 23 mugs, so that would be 23 out of 77 for the first option. Not replaced means now there's only 22 mugs in 76 baskets. And then there were 3 baskets, so that's going to be 21 out of 75. When you plug this in, you get 0.0242. So you have a 2.42% chance that you'll select 3 baskets with at least a mug if you don't replace. All right, I'm going to kind of do this a little weird. I'm going to put E up here. You can continue on in your notes, but I want to keep this chart here as well so I can kind of show you where I'm getting these numbers. So E says if 3 baskets are chosen at random and not replaced, none contain mugs. All right, so if there's 23 that do contain mugs, I find it to be easier to do 77 minus 23 rather than adding all these numbers up that do not contain mugs. So 77 minus 23 would be 54. So there's 54 options that do not contain a mug, but there's still 77 total. It says I want 3 baskets not replaced, so that means the numbers will go down by 1 until I have 3 of them. So then this comes out to be about 0.3391. So a 33.91% chance that you'll get a 3 baskets with no mug. Last question, part F. If 3 baskets are chosen at random, not replaced, at least one contains a mug. So this is at least one. So remember, the easiest thing to do is to find, so a probability of at least one is equal to 1 minus the probability of none. So what's the probability that none of them, is it none contain a mug? So if there's 23 that contain a mug, none of them would be 54. So this would be 1 minus 54. Oh, I forget they said they chose 3 baskets. So I was about to do this all out of 1 basket. So they chose 3 baskets. So this is the probability that none of them are mugs. So then that would be 1 minus 0.3391, which comes out to 0.6609. So there's a 66.09% chance that at least one of them will have a mug in 3 gift baskets if you do not replace. All right, that will pretty much wrap up chapter 4, talking about probability and counting rules. If you ever need any more examples or help or anything like that, please reach out. I do not mind making more. Other than that, I will see you in the next video.